Example 6. 20,000 people were tested for boredom tolerance. Possible test scores were 0, 1, 2, 3, 4, 5, and 6. The frequency or count for each score is shown in the frequency table below. We're going to let X be the score of a randomly selected subject. So X is a random variable. Then, of course, P of X is the probability of getting that score when you randomly select one of the subjects. We're going to compute the probability distribution for this random variable X. Now, I think the best way to think about this is to think of the sample space of our experiment. And when I say experiment, what I'm talking about is the experiment of taking a person randomly out of the set of test subjects. So the sample space is the set of test subjects, in other words, the people. What the frequency table below tells us is how many of those people had a particular boredom tolerance score. Now, since the boredom tolerance score is numerical, that's why we can just use the score itself as our random variable. We don't have to come up with number of heads or something like that. So let's fill in our probability distribution for the X value 0, in other words, the boredom tolerance score 0. What's the probability that when we randomly draw a person out of our set of test subjects, that person had a score of 0? Well, there are 1,400 people in the sample space, in other words, in our set of test subjects, that had that score, and we'll divide by the number of test subjects, which we were told was 20,000. So what I'm thinking about here is we have this event, and the event is that when I select that person, I select a subject with score 0. Then what's the probability of that event happening? Well, it's the number of outcomes or items in that event divided by the number of outcomes in the sample space. So N of E in this case is the number of people that had score 0, because the event is selecting a subject with score 0, and the number of items in the sample space is 20,000. So we use a calculator to get a decimal for that, and we get 0.07. So we're just going to go down the list, filling in all of these. For line 2, the event I'm thinking of is selecting a subject with score 1. The probability of that happening is taking the 2,600 people in our sample space that had that score, divide by the total number of people in our sample space. Of course, we use a calculator, so we get 0.13. For X equals 2, we're going to take 3,600, divide by 20,000, and we get 0.18. And then going on down the line, we'll have 6,000 divided by 20,000. That is 0.3. $4,400 divided by 20,000 is 0.22. And the last two are 1,600 divided by 20,000 and 400 divided by 20,000 And those are 0.08 and 0.02. These calculations that we just did might seem familiar to you. And good job if they did and you thought, hey, this is a lot like calculating relative frequency. Because in fact, it's exactly like calculating relative frequency. Remember when we did relative frequency? We took the number of individuals in a sample that had a certain characteristic, in other words, their frequency, and we divided by the total number of individuals in the sample. Well, that's really what we did here. So it can be helpful to remember that probability in this kind of situation is really just the same thing as relative frequency. And I think as we mentioned when we were doing relative frequency, that's also the same number or calculation as getting the proportion of the population that has that characteristic, or proportion of a sample that has that characteristic. We can also make a probability histogram, and I've just gone ahead and done that for us, so that's what our probability histogram looks like. A couple of features of probability distributions that I want to point out here is a probability has to be assigned for every value of x. You can't just skip some. You have to calculate a probability for everyone. Now, sometimes the probability might be 0. That's okay. That's part of the information we need. Also, the probabilities must add up to 1. And by the way, that's a good check when you're making a probability distribution, is to just double check that indeed they do add up to 1. So I'm going to check that right now for ours. And yep, sure enough, they add up to 1.0. One thing I should maybe mention that I think we probably mentioned back when we were doing relative frequencies, and that is if you had to round off any of your decimals, you may end up with something like 0.99 or 1.01 or something like that. And that would just be due to rounding error. But why is it that the probabilities need to add up to 1? Well, it's because the probability of an entire sample space is 1, and that variable x has to be assigned to every single outcome in the sample space. Therefore, the various values of x encompass the entire sample space, and that's why those probabilities have to add up to 1. I'm going to leave you with a build your understanding problem. This is another coin toss one, so it'll be very similar to the coin toss example I did a little earlier. I'm going to help you get started by helping you with the sample space. So if we toss a coin 3 times, possible outcomes are heads, 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 tails, heads, tails, heads, tails, heads, heads. So that's all the possibilities, first with 3 heads, then all the possibilities with 2 heads, 1 tail. And then what about having 2 tails and 1 head? So I could have head with tails, tails. I could have tails, heads, tails. Or I could have tails, tails, heads. And then last possibility is 3 tails.